Welcome back to Learn with Onsen, and today we're going to be going over factorials and the N-K theorem. A factorial is noted as an exclamation point, and when we see an exclamation point in English, the first thing that comes to mind is excited and happy in a story, but in math, it means something else. In math, a factorial means the product of an integer and all the integers and all the product of the integers until we get to 1. So, as an example, 3 factorial would be exclaimed as 3 times 2 times 1 because we take the number, which it is, and that number would start, and we go until we reach 1, and we multiply all of that together. Let's just do one more example. Another example of a factorial is 4 exclamation point, which is 4 times 3 times 2 times 1. This is because the 4 is our beginning number, and we move down by we go to the next whole number, and we multiply them all together until we reach 1. So 4 factorial would equal 24, because 4 times 3 is 12, 12 times 2 is 24, and 24 times 1 is 24. Now, let's start moving on to the problems. So our first problem is, find all the orientations of the word the. Now, in simple casework, we could find all these orientations by T, H, E, T, E, H, E, T, H, E, H, T, and H, E, T, and H, T, E. Now, although these are in words, we're still going to count these as an orientation of the word the. So, the is a simple 3-letter word, so in casework, this can be solved very easily, but there is a formula that we can use for a problem similar to this. Instead of finding it like this, we can make 3 underlines. This first underline is going to be for the first letter of the word, the second underline is going to be for the second letter of the word, and the third underline is going to be for the third letter of the word. So this first underline, we're not going to apply it to a single letter, but we're going to apply it to a combination of letters. So this first letter could be a T, it could be an H, or it could be an E. We don't know which one it is, but we know that there's going to be 3 possibilities, so we can write the 3 at the top. Our second letter of the word, it can be T, an H, or an E, but one of these letters is cut out. So for example, let's say we use T at the start, so T is not an option anymore. We'd only have the options H and E left, which leaves us with 2 options now for this second letter. So we'll write a 2 up here. And this third one, we will write T, H, E. But we cut out, let's say this one's in E. So now we use the option T and option E, which leaves us with only 1 option. So this is a 1 here. Now we take all of these and we multiply them by each other. And 3 times 2 times 1 equals 6. So there's 6 combinations for this. This should remind you of something. If we go back to the definition, a factorial means the product of an integer, and our integer is 3, and the integer of all the products below it until we reach 1. So 3 goes to 2, which goes to 1. So this actually is just 3 factorial. Now we can look at this in a second problem and use more confusing, where casework is a lot harder to be applied here. Let's think of the word please as an example. P-L-E-A-S. Please. Yes. Please is how many letters? 1, 2, 3, 4, 5, 6. 6 letters. So we'll draw 6 underlines for this one. This first underline can be any of the letters in please. So it has 6 options because it can be a P, an L, an E, an A, an S, and an E. in this next underline, we're going to remove one of those options because we previously used it in the example. So now, let's just say this first letter was an L. So we're going to remove the L here, and our options would be a P, an E, an A, an S, or an E. So we'd have 5 remaining options. And if we go like this going forward, where we keep removing one option, we'd be left with 6, 5, 4, 3, 2, 1. And as we did in the problem, we'd multiply them all together. And if this looks similar, it should, because the definition of a factorial means the product of an integer and all the integers below it until 1. So if our integer is 6 and we go below it by a whole number until we reach 1, it's exactly this, our 6 factorial, which is equal to 720. And the reason I'm saying the definition so much is because I want it to be a concrete part of this video, because learning requires multiple takes at something. You're not going to learn something if you just go over it once, so you may hear the definition of factorial more in this video. Let's take that number that we remembered, 720, because although you may think we're done with this problem, we're not done just yet. 720 is the total possible nations of P, L, E, A, S, E. But we're adding too many combinations because we have double E's. Since we're going on the number of options and we write out a random example as P, E, A, E, S, PS, we don't know which E this is. This could be E1 or E2 if we define the E's, but if we write out another P, E, A, E, S, it's the same thing, but this could be the second E and this could be the first E, leading to interchangeable results. So although it looks the same, this one P's counts for 2 options. So we have to take our number, our total 720, and divide this by 2 because of all the interchangeable P's that are in there. And 720 divided by 2 is 360. So although many thought it was 720 for our total is actually 360. Now, as we can use basic factorials, we'll do one last problem that will be a little harder. Let's think of the word algebra. This has 1, 2, 3, 4, 5, 6, 7 letters, so we'll do 7 underlines. The first underline could be any of the letters A, L, G, E, B, R, A, so we can put 7 here. Next, we'll take away one letter, leaving us with 6 options. We have one less letter now because we already used 2, so we have 5 options remaining. And this goes on until we have reached 7, 6, 5, 4, 3, 2, and 1. So now we multiply them together. And just for the sake of learning, I'm going to go over the definition of factorial again. A factorial means the product of all integers and the integer below it until we reach 1. So if we say 7 as our integer, we go by every whole number from 7, 7, 6, 5, 4, 3, 2, 1, until we have reached 1. So 7 factorial, so also written as 7 factorial. 7 factorial equals 5040. But if you noticed, algebra has 2 A's. So as we need to do this time, if we write the example, we don't know if this is A1 or A2. So this could be interchangeable. So now this one could be A2 and this could be A1. And as we have these interchangeable results, this happens for each combination since the A is applicable in each combination. So we take this 5040 and we divide it by 2 again, leaving us with 2,520 as our final number. Now we're going to move on to the n choose k formula section of this video. So n choose k is a formula that is written like this. It's like a fraction, but we don't have the line under, and it's in parentheses. This n choose k stands for n factorial over k factorial times n minus k factorial. The formula for n choose k, where you're wondering it's applicable, I'll leave it up here. Let's say we have 3 dots. That's 5 dots. This is dot 1, dot 2, dot 3, dot 4, and dot 5. And the question asks us, how many ways are we able to pick 3 dots out of these 5? So we pick 3 dots. So for an example, we pick these 3, or we could pick these 3 dots. How many ways can we do that? Well, we can use this by using the n choose k formula of 5 choose 3. So as we use our formula, it's n choose k, and we're going to write it as 5 choose 3, because we have 5 choose 3, because we have 5 options, and we have 5 dots, and we're finding 3 ways to pick on one. So if we apply this to the formula, it would be 5 factorial over 3 factorial times 5 minus 3 factorial. And we can simplify this by saying 5 factorial over 3 factorial times 2 factorial. And now we can expand these so we can simplify easier. So the 5 factorial, we're going to write it as 5 times 4 times 3 times 2 times 1. And this is all going to be divided by 3 factorial, 3 times 2 times 1, and 2 factorial, 2 times 1. So this 2 is going to cross out with this 2. This 3 is going to cross out with this 3. And this 4 is going to cross out with this 2, leaving us with a 2. So our final thing that we have is 5 times 2. And as we know, 5 times 2 equals 10 with basic arithmetic. So if you're wondering how many ways we can get 3 balls out of 5, it's 10. Now, we're going to look at more problems where this can be applicable. Now, this problem is going to be a little more difficult, but it's going to showcase where n choose k comes into play and how easily you can mess up problems if you're not doing this right. This is a long problem, so stay with me. The problem is, Lisa shakes her piggy bank, which contains 5 quarters and 5 nickels. She shakes her piggy bank until 5 coins fall out. What is the probability that the sum of the coins that have fallen out is 85 cents? Now, this is a long problem, so let's take some time to process. We're going to have 5 quarters. I'll put that as a Q for short, and 5 nickels. And we want to get to 85 cents after 5 fall out. So, the only way that we can get 85 cents with using 5 quarters and 5 nickels is a quarter, a quarter, a quarter, a nickel, and a nickel, which is 75 cents plus 10 cents, or 85 cents, which is the number we want to get. So, the first thing that we'd be trying to do is, what is the probability of getting 3 quarters out of the piggy bank? So there's 10 total coins, so our denominator is going to be 10. And we want to get a quarter, and the problem stated that there were 5 quarters in the piggy bank, so a probability of getting a quarter out of 10 is 5. Next, we want to get another quarter, but since we've already taken one out, our denominator is going to be 9, and since we've already taken a quarter out, our numerator is going to be 4. And we can cross these out so we don't skip any. Our next quarter is going to be a denominator of 8, because we have taken out 2 coins and a numerator of 3. Now that we're done with the quarters, we can move on to the nickels. The nickels, there's 5 left since we have not taken any out, but we have taken out 3 coins, which leaves the total number of coins to 7. And we take out another nickel, which there's 4 remaining since we've previously taken 1 out, and there are 6 coins remaining since 4 have been taken out prior to this. Now, instead of me going through the simplification process, I'll just simplify it for you and cut to where this is 5 over 126. Now, instead of boring you, and now most people think this problem's over, but it's actually not. Because although we selected quarter, 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 nickel, nickel, all of the order we pick them in is interchangeable. So this is where the N choose K comes in. Because casework for how many ways can we orientate quarter, 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 nickel, nickel would take too long. We can just say there are 5 total objects. And in these 5 total objects, we want to see how many ways we can orientate the quarters. And there are 3 quarters. We don't have to worry about the nickel part of this because this is already changed for us as we change the quarters. And as a reminder, the formula for N choose K equals N factorial over K factorial times N minus K factorial. Now I'm just going to erase this so we can be a little clearer with our writing. So 5 over 3, if we put it in the formula, is 5 factorial over 3 factorial and 5 minus 3 factorial. Now we can simplify this and express it fully by saying this is 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1, and 5 minus 3 is 2, and 2 factorial is just 2 times 1. Now we simplify this. 2 divides the 2, 3 divides the 3, 1 divides by 1, and the division doesn't really matter. And then the 4 divides by 2 to make it a 2. We're left with 5 and 2. So, according to basic arithmetic, 5 times 2 equals 10. Now, we take what we knew about what is the probability of getting the quarters out, which is 5 over 126. And we take this 10, because this is the ways we can orientate them, and we multiply this by 10, which gives us 50 over 126. So the number of ways we can take out 5 coins where there's 5 quarters and 5 nickels and get 85 cents is a 50 over 126 probability. Thanks for watching, and I hope you learned something from this.